f of x is said to be continuous, at a point x equals to a if 1, f of a is defined, 2, limit of the function as x approaches this point a exists, and the last condition 3, the limit as x approaches a of f of x is given by f of a. So that's the definition of continuity, continuity of a function at a point x equals to a. So the first condition is that the function must be well defined at a. That simply means that if I pick the value a, I replace it to the function, I get a number, or I get something that calculator will give me a number, not math. And then the second condition, if I evaluate the limit of the function as x approaches that particular point a, then I get a number also. And then the last condition is that the function at a must be the same as the limit of the function as x approaches the same point a. Come again? Yes, yeah, the limit of the function as you approach that point should be the same as the value of the function at the same point. So we give an example. Test whether f of x given below is continuous. So this is the function. F of x is given by x squared minus 25 over x minus 5 if x is not equals to 5 and 10 if x equals to 5. Yes? Is x squared minus 25 over x minus 5 if x is not equals to 5. Equals to 5. If x is equals to 5, yes. It's 10, yeah. This 10. It is the second definition of f of x. This function is piecewisely defined. That means that the function is defined by two different formulas on its domain. Yeah, it's the same way we wrote the absolute value function. So there are two formulas. If x is greater than or equals to 0, if x is less than 0. So all this expression on 10 are still defining the same function. So I just read the question, I'll explain. Good. So the first step, so what is the point of reference here? The A that is being said in the definition. A is 5. 5 is the point of reference, okay? Yeah, 5 is a point of reference. Now, what is f at 5? What the value of the function at x equals to 5? Yeah, that's what I'm asking. It's 10. We don't need St. Peter's to tell us it's 10 because there's already condition is given here that f of x will give you 10 whenever x is 5. So when I put here 5, then I'm going to apply the second line. Okay? Yeah. So we say f of 5 is 10. So which means this one exists or is defined. So which means that the first condition in the definition of continuities are already holding water, that the value of the function at the point of reference is or that exists and the value is 10. Next is to find limit. No, they must all be right. All this must be true. If one of them, if at least one of them is not true, then the function is not continuous, becomes discontinuous. So all the conditions must be satisfied. So the first one is okay. The value of the function at 5 is 10. So the first condition is satisfied. Yes? So now, remember when you say x is approaching 5, does not necessarily mean that the x is 5 already. So yes, that's what I'm explaining, that when you say limit of f of x as x approaches 5, does not necessarily mean that we are already at 5. It simply means that the value of the function as we get closer and closer to 5, we may not necessarily be at the point itself. Okay? So which formula are we going to pick? Are we going to use 10 or we are going to use x squared minus 25 over x minus 5? Forgetting the limit, we are going to use the first formula. So remember, when we say x approaches A, does not necessarily mean that we are at the point A. We are simply trying to see what is happening to the function as we get closer to the A. So to get the limit, you are going to use the first definition of the formula, not the second one. So limit, ask. Yeah. This one function, f of x, defined by two formulas. So this is what we call the piecewise defined functions. This was the first thing we discussed in this course. Types of functions. Hello. So this is one function defined by two different formulas on its domain. That it is 10 whenever x is 5. And when x is not 5, then this is what we have. Yeah. How do we evaluate this limit? By which method? Yes, explain. Mm. Mm. Yeah, we use factorization, okay? Because if we do direct substitution, we get in terminate form, 0/0, which is not defined, okay? Yeah, so we'll use factorization. Limit as x approaches 5. We have x minus 5. Ask. So you are mixing terms. It's good that you are asking it now. You are not carrying the problem ahead. Remember, what we have been discussing in the previous class were limits as x approaches either plus or minus infinity. That's the only way you are going to do those things of dividing every term by highest power of x in the denominator. When x is not approaching infinity, you don't do that division. Don't mix yourself up. The only time we divide each term by the x with the highest power in the denominator is when we have seen that x is approaching either plus or minus infinity. That's the only way we do that computation. If x is not approaching either plus infinity or minus infinity, that is not what we do on evaluation of limits. That's why it was a special section, and we called it limits at infinity. So there's a special way we deal with them. But when x is not approaching either plus infinity or minus infinity, we do not do that exercise of dividing the term in the numerator and denominator by x with the highest power in the denominator. So, yeah, so you should be able to know that. So the only moment you think of that division is when you have seen either plus infinity or minus infinity. Otherwise, we don't do that for any other limits. So, George, so good. So we cross this and we cross this. So this is the limit as x approaches 5 of x plus 5. So what will be the value of this limit? 10. So 5 plus 5. So we are saying that, yeah, so limit as x approaches 5 of f of x is giving us 10. So which means that the limit exists. So what is the third condition? So we are confirming the steps or the conditions that must be satisfied for us to conclude that the function is continuous. Yeah. So since f at 5 is 10, and this 10 is the same as limit as x approaches 5, of f of x, we conclude that f of x is continuous at x equals to 5. So it is true that that given function is continuous at x equals to 5. So this is the condition 3, where we say that the limit of the function and the value of the function at that point must be the same. So this is the third condition. And actually, you are the one who has already seen it, that the answer we are getting for the limit is exactly the same answer we got at 5. So when that is the case, then it becomes true that the function is continuous at that particular point. Yeah. So this is condition 3. Okay. That's a good question. So we are going to do next example to see when the limit doesn't exist. Yeah. She's absent, so she's having some problems. Okay. Okay, so maybe before we do an example to explain what you're asking, when we say that probably the process is messed up on limits, let's okay. So let's repeat the same for this question. So just for continuity, given f of x is given by x squared minus 16, x minus 4, if x is not equals to 4, and 10 if x equals to 4. Okay, so we can change this to be a different number. People will think that it was 10. So let's say, let me put here 15. You can as well put 10, there's no problem. But, okay. Yes? Okay, yes. You see, people can confuse that it's always, the lower number must always be 10. So that's why I changed to 15. But even if you put 10, there's no problem. So yes, past condition. So what is our A in this case? A is 4. The test points is 4. So you are saying this, they say x equals to 4, x equals to 4. So 4 is the reference point. So what is it true that f at 4 is defined? Whose value is 15. George, are you able to see that? Yeah, we do not need St. Peter's to tell us that this is a formula that applies when x is 4, because the condition is clearly stating that f of x equals to 15 if x is exactly equals to 4. So when x is 4, you use the lower formula. Then number 2, so this is well defined. So the first condition is okay. Condition 2, let's get the limit as x approaches 4 of the function. And remember, when you say x is approaching 4, does not necessarily mean that you are already at 4. So this will be the same as limit as x approaches 4. F of x, which formula do we use now? Yeah, so x squared minus 16 over x minus 4. Factorize, because by direct substitution, we are going to get things which are not defined, 0 over 0. So this will be limit as x approaches 4, x minus 4, x plus 4, x minus 4. Yes, this one and this one cancels out. So we'll have limit as x approaches 4 of so what do we end up with the limit? 8, correct. So that means that limit as x approaches 4 of this function f of x is 8. So the limit exists. The answer is 8. Now, is the value of the limit the same as the value of the function at 4? No. Is so the value that a given function appears to be taking as you move closer and closer to that value of x. The value the function appears to take as you move closer and closer to that x value. So this means that as we get closer and closer to 4, this x squared minus 16 over x minus 4 gives us 8. Yeah. But we see that f at 4 was given as 15, which is not the same as 8, which we are getting as the limit as x approaches 4 of the function f of x. So what is the conclusion? So the function is not continuous. So therefore, f of x is not continuous. Ask. So this is the value of the function at x equals to 4. So that is f of 4. Okay? And then from our calculation, the limit of this function is given by 8. Okay? And you see the 15 and 8 are different numbers. Yes, as x approaches that number 4. Condition 3 is not satisfied, so therefore it fails the test for continuity. So remember, all of them must be satisfied. If at least one of them is not satisfied, then the function is not continuous at the specified point. Agnes? Agnes, you're waiting for your question. Okay. So this, notice that if we redefine f at 4 to be 8, then the function becomes continuous. If we redefine good, at least you are seeing that. Good. So notice that if we redefine the function as the value of the function f at 4 to be 8, then the function becomes continuous at x equals to 4. This is what I mean. If you rewrite f of x as x squared minus 16, x minus 4, if x is not equals to 4, and you put 8 here, then all the tests of continuity will actually hold. So such kind of discontinuity, so a function which is not continuous is said to be discontinuous. So this is an example of a removable discontinuity. So I was saying that you can, because remember the number given in this position in the problem was a constant, which is 15. But that 15 was not tallying with the limit of this function. As we approach 8, yeah, so approach 4, which was 8. So instead of 15, if you replace 15 by 8, then you'll see that the value of the function at 4 will be agreeing with the limit at that point. So if you have that allowance of replacing a constant to a different number, which is the same as the limit, then we say that that kind of discontinuity is removable because you can redefine the function such that you replace a constant in the place of f at that given point A for the value to match with the limit. But sometimes that is not necessarily true. For instance, that's why I'm saying that that's why we are concluding that the function is discontinuous or is not continuous at x equals to 4. So this is just another way of redefining the same thing for it to be continuous. So this number must agree with the limit, which was 8. These are constant. So when you change the constant 15 to 8, is what will make the value of the function agree with the limit. Yeah. Okay, so let me give you number 3, test for continuity for this function f of x equals to 2x plus 3 when x is less than or equals to 2 and 10 when x is greater than 2. Yes. Or you want to do it on your own? Okay. George, remember this was your section. Okay, so we talked of these signs in 120. So these things are usually interrelated. These inequality signs. Okay, so so the first thing, let's agree. What is A? The point of reference is 2, okay? Now, huh? Okay, so George, this is where we started from. You see the previous 2 examples. You were the one who told us that in this case, A is 4 And in the previous example, you are the same person who told us that in this case, the point of reference is 5. The number being tested is that we are doing things with respect to that number. You see here is not equals to 5, here is equals to 5. So the reference number is 5. Yeah. Now, so what is f of 2? Well, the first condition is to test the value of the function at a. F of 2 is 10. George, do you agree or disagree? Okay, so my question is just to ask you, what's the value of the function at 2? Yes. 10. For the first time, I've beaten you. Okay. How do we get, how I knew you'll tell me the answer is 10. I had, I had already predicted that you'll tell me 10. Don't disappoint your high school math teacher. I knew you'll tell me 10. Okay. Probably let me explain here. This one I have 1. So this is formula 1. This formula 2 that define this function f of x. So we have agreed that our reference number is 2. Okay. So remember 2, there are things which are to the left of 2 and things which are to the right of 2. Okay. So 2x plus 3 will be used when value of x is equal to 2. So this other side, I'll have 2x plus 3, including the 2 value at 2 itself. If I am from 2 and I go to the left, the formula which will be used for f of x will be 2x plus 3. Okay? These are the formula tells us that I will always get 10 whenever x is greater than 2. So when I'm moving from 2, going to the right-hand side, the value of the function will be 10. So, yeah. So which means that the value of the function at 2 will be defined by which formula? F1 or F2? F2. Remember F2, there is a strict inequality here. X is greater than 2. So here you are not taking 2. But here x is less than or equals to 2. So the formula that allows you to evaluate f at specifically 0.2 is this first formula, not formula 2. Okay? I hope now you see why you are doing 3 courses at the same time. Yeah, so you have to really, one has to help you to interpret things in other course. So this is x less than or equals to 2. So this is the condition that allows you to get the value when you are at 2. But this cannot help you because it's strictly greater than 2. Okay? So what's the value? Seven, because you're going to have 2 times 2 plus 3. So the answer will be 7. So it's actually defined. So there's no problem. Condition 1 is satisfied. Okay? Yeah. George, are we together? Good. So what is the second condition, George? Yes. Is to get? Correct. So we need to get limit. So limit of the function f of x as x approaches our number is 2. So what's the value of the limit? Hmm? 11. 7. Agnes, do you agree with that? The other is 7. This one I've won everything. Okay, last time, okay, before you reclaim yourself, last time we introduced limits and our discussion on the computation of limits, or even after definition, and then how explaining how to evaluate limits of functions. We say that limit will always exist whenever. Okay, if I'm moving from left, this is point A, and someone else is moving from the right. When do we say that limit at point A exists? What must be the condition? And then, so when will you say that the limit exists at A? So when you're moving from the left, we write this one as limit as x approaches A. You put a minus sign here. Does not mean that you're negating A, but you mean from left of f of x. And this from the right, you write limit as x approaches A from the right-hand side. You put a positive sign here of f of x. So what will happen to those two limits for us to conclude that limit at A exists? Okay, so at the end of the day, when we are evaluating, actually, the number doesn't change. The negative and positive sign are just used to show direction. Negative means from left, positive means from right. Okay, it seems that that one didn't sink in. So let's remind you. So remember that limit as x approaches a number A of a function f of x exists if and only if limit as x approaches A from the left of the function is the same as limit as x approaches A from the right of the same function. So both the left-hand limit and the right-hand limit must be the same. So in this case, you're not just going to pick 7 or 10. You are not going to guess. You have to get the left-hand limit and also get the right-hand limit and see whether the two actually agree. There? Okay. So what is the left-hand limit? Left-hand limit. Okay, so the question is, the left-hand limit, the question is, which function are we using, which formula are we picking? Is it F1 or F2? F1, because F1 is what tells us that f of x is given by 2x plus 3 if x is less than or equals to 2. You can clearly see, even if you draw a small number line here. So this is the number 2 is the reference. So which means that whenever x is on this left-hand side, the formula that applies is 2x plus 3. So whenever you are to the left of 2, or if you want to approach 2 from the left-hand side, you'll be using this formula 1. So this is the function that you use for left-hand limit. And which function do we use for right-hand limit? F1 or F2? F2, correct. Because remember, the condition here is that f of x is 10 whenever x is more than 2. So if this is number 2, then what is more than 2 is to this right-hand side. So this is 10. So this 10 is what will help you to calculate the right-hand limit. This 2x plus 3 is what will help you to calculate left-hand limit. So you are going to say limit as x approaches 2 from the left-hand side of f of x will be the same as limit as x approaches 2x plus 3. I'm not sure. Who knows? Yes, we're still testing. So this will be it happened then. Yeah. So this will be left side. So what when you substitute, you'll have 2 times 2 plus 3 to get 7. So this is what you call the left-hand limit, okay? Yeah. So right-hand limit. Yeah, you are partially right, only that now you are to explain how you are, which limit are you getting? So limit as x approaches 2. So remember, when I put plus sign, does not mean that I'm now changing. If the number is negative, I'm making it positive. It is the same number. The plus only shows the direction. Yeah. So limit as x approaches 2. So which function do we use? So remember, we are still using this, the same problem we're solving. So that's the condition, but which formula? Which is 10. So when x is more than 2 is 10. So this is from the right. So the function is 10. And what will be the value of this limit? 10. So is limit as x approaches 2 from the left of the function equals to limit as x approaches 2 from the right of f of x. They are not, because you see, here we are getting under 7, and the other side we are getting 10. Okay? So not oh. So then now, so the conclusion is that limit of the function does not exist because the left-hand limit and right-hand limit are not giving the same number. So this implies that limit as x approaches 2 of f of x does not exist. So we say does not exist if the left-hand limit and right-hand limit have different values. Yeah, so what's the conclusion now for continuity of that function as 2? The function is not continuous, yeah, at x equals to 2. Therefore, f of x is not continuous Remember, don't confuse yourself. This is the whole function f of x. It's only that now this function happens to be defined by different formulas on this domain, but the name remains the same. This is f of x. Yeah. So the only variation is that this f of x happens to be having two different formulas on its domain when x is less than or equals to 2 and when x is greater than 2. But the name of the function remains f of x. Yeah. Yes. Function and formula. Oh, the function, everything here. Now remember, I was calling this one F1, F2 for illustration. They are not part of, you don't have to put them there. I was only trying to explain that this f of x, there are two things which define it, 2x plus 3 and 10. And 2x plus 3 when x is less than or equals to 2, 10 when x is more than 2. So I called f1 and f2 just for convenience to know that there's two things here defining the same f. So there's nothing special with that. Okay. That's an interesting question. So f of x happens to be defined by two functions, if I may say. There's this linear function and there's this constant function. Okay. George, were you in class? Were you in class when you were discussing about different types of functions? I love your honesty. Okay. So know that a function can be defined by other functions on this domain. So you are just right that are these formulas or are these functions within a function? A function can be defined by other functions in its domain, like what we have here. F of x has been defined by the function 2x plus 3 and also by the function 10. Yeah. Okay. The conditions, these conditions, yes. Yeah. Good. So then the conclusion will be f of x is not continuous at x equals to 2, since the third condition is not satisfied. The limit, since the second condition, since limit does not exist. Immediately you find that one condition is not satisfied, you stop. That's enough to show that the function is not continuous. No, this type of discontinuity is not removable. This kind of discontinuity is not removable. Where the limits now, the case whereby limit does not exist is not described as removable discontinuity, but it's described as jump discontinuity. So this is an example. Yes, of jump discontinuity. So jump discontinuity means that the limit of the function as we approach that particular reference point A gives you get different values of limits from the left-hand side and from the right-hand side. So that's what we refer to as jump discontinuity. Jump discontinuity cannot be treated. Yeah, so this the only one that can be corrected is the removable, where the problem is on the definition of the value of the function at that point. But when there's a problem with limits, you can't correct that discontinuity. It remains the way it is. Okay. Yeah. So maybe if I do this, Let me say this is a graph of an arbitrary function. I have, say, this point 2, and I have this. No, I'm stopping. I'm still in office. I need to be going home. I'm in office now. I need to go home. I'm in town, Jerome. So, yeah, say this is 19. I'm in office, so we are finishing up. So say this is 19, and then say I have at this point be 24, and let's say I have so let this value be say negative 29. So someone can draw an arbitrary graph, and you may be asked to compute some terms, compute the limits and discuss the continuity of the function just from the graph. So for instance, if I ask you, what is the limit as x approaches 2 from the left-hand side of f of x, this graph? Another question, limit as x approaches 2 from the right of f of x. And another question, what is the value of the function at 2? And what is the limit of the function as x approaches 2? Is it continuous? At x equals to 2. Who is willing to give us an answer to any of these questions? So let me call this is A, this is B, this is C, this is D, and this is E. Pick any of the parts and try to tell me the answer that you think is as per the diagram. Mm. 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 Okay, I just want the answer. Just give me the limit first before to conclude. To conclude continuity at x equals to 2 is it's a complicated process if you don't know part A, B, C, and D. I need a number. What is the limit as x approaches 2 from, for which part? Remember, I've labeled them A, B, C, D, E. A, the answer is 2. George, you agree? You don't have to calculate anything. 2. Okay. George, true, false? Yeah, even me, I'm worried where the two is coming from. I can't see. Agnes, how are you getting to? Okay, so we are not happy with F. Okay, so let me delete that. So go to any other part then. You are happy. So what's the value of B? Base 2. You are sure that base 2. I just thought that probably maybe by drawing it will help you to answer the question. So let this be a boy and let me draw a girl here. Yes, yes, yes. Mm. You remember, yes. Remember the limit of values on the y-axis is not x-axis. So remember, we say limit of f of x. Huh? Remember, f of x is the same as y. So y equals to f of x. So the values of the limits are obtained on the y-axis. X-axis is what gives us the point of reference at okay. Okay, so there's a boy and a girl, okay? Okay, believe that these are boys and these are girls. So please trust the process. The boy is, remember, all this graph defines one function. So this was defined function. Um, all this can. So how do we get the right hand limit? So remember, when you say x approaches a, then plus, this means this is the right hand limit. Are we going to use the root of girl or the root of the boy from my diagram? Who is going to get the right hand limit? Is it the boy or the girl? Boy. So, and remember the reference point is this line x equals to 2. So the arm that gives us the right hand limit is the arm that the boy is walking along. So as the boy moves closer and closer to the line x equals to 2, what is the value of the function? 19. You don't need St. Peter's to tell you that. Yes. Yes, yes. Remember, Agnes, 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 but I didn't hear you saying anywhere 24. Or George, do you hear? Did she say 24 anywhere? Okay, but remember that 24 is not fashion. 24 is not fashion. If you are very keen on when you are discussing a piecewise defined functions, the way 24 is written, this graph, there's nothing that is fashion on the figure. Everything has a function as to why it is the way it is written on the diagram. So part B, what is f of 2? Okay, if you are not happy with B, you can go to C, D, or E. Let's answer C. Mm. You are not able to see this. I've labeled this. Are you not? You are not able to see this question. This questions. Huh? Okay, that is wrong. At C? Yeah, the answer two is wrong. Wrong answer for part B. I okay. What is the meaning of question in C? This question C. Okay, Agnes, go ahead. I love Georgia. I love your question. Georgia has a good question, Agnes. Georgia, I support you. Yeah. So Agnes, this is the simplest way you will make it. So the interpretation of limit of f of x approaching 2. So remember, I've said that we are not, this thing is not interpreted in terms of positive and negative. Please, this sign I'm writing here doesn't mean positive or negative. These signs of minus and plus, they mean direction, whether from right or from left. So when I write x approaches 2 and I put a plus here, I mean I am moving towards 2 from the right-hand side. And this means I'm moving towards 2 from left-hand side. It does not mean minus 2. So in terms of your explanation, you will explain it without using plus sign, without using plus and minus signs in your explanation. It's saying this means you are approaching 2 from the right-hand side. This means you are approaching 2 from the left-hand side. That's what will make George to understand what is happening here in A. That this means limit of the function f of x as x approaches 2 from the right-hand side. And there are these two arms. Remember, this is the line x equals to 2. So we want to see how do we move toward this line from the right-hand side. And everyone will be able to see that this is this purple path. This is a path that we need to follow. To reach the line x equals to 2 from the right-hand side, you need to take this road in purple color. So that's where the 19 is coming from. So you are moving along this path, and then as you get closer and closer to 19, closer and closer to the line x equals to 2, the value of the function is really at 19. So that's what we have. Remember, this value is not exactly at 19, but it appears to be getting closer to that value 19. Okay? Will be? Yes, C will be negative 29. D, what makes you to say it's negative 29? Okay, maybe Agnes, help Can you explain why you are getting the C to be negative 29? Yes. So this means X is moving towards 2 from left. And left in math is left. Right is right. It's not like biology where sometimes they reverse. So this is the value we are moving towards 2 from the left-hand side. And this is the pink path that will be doing that case. This is the line X equals to 2. So we are moving towards the point X equals to 2, but from the left-hand side. Mm. Okay. The thing, George, what is happening here is that the final answer of the limit is red on the y-axis. The limit value is red on the y-axis. That's why when we were introducing limits, we explained that limit of a function f of x as x approaches a point A is L if given a small positive distance epsilon, there is always a delta which is also positive, such that f of x minus L is less than epsilon, provided that x minus A is less than delta. And this is what we drew, that if you have an arbitrary function, there is a point you are calling A, then L is red on the right and on the y-axis. So the limit value is red along the y-axis. Okay?